Let me start by saying thank you for all the organizers and the program committee chairs for inviting me here today. It's a real pleasure for me to be here, especially this is my first conference in the COVID era, so really happy to be here in person as opposed to be screaming at a Zoom screen and talking to people over Zoom. So thank you again. I also want to give a brief shout out to, in the room full of engineers and scientists, to folks who really developed the COVID vaccine so that we could all be here in person today and enjoy this conference. So the focus of my talk today is a precision scaling roadmap for AI inference and training systems. And I'm really happy to be here to be presenting this work on behalf of a wide spectrum of folks who have contributed to this work at IBM, and also a lot of our academic colleagues. We've also had the opportunity to collaborate on this work with a lot of different folks across the industry through an ecosystem that we established a few years ago called the AI Hardware Center. So thank you all of you for helping us get here. The focus of my talk today is to look at the precision scaling powered performance roadmap for AI inference and training systems. And what I hope to do today is to walk you through some of the key innovations that have enabled dramatic increases in performance and power efficiency for AI hardware. I'll also spend a little bit of time talking about what's coming down the road in terms of the kinds of innovations that we expect to see in the next decade. So I think, as I'm sure all of you know, AI in general and deep learning in particular have had amazing success in a wide spectrum of application domains, including speech, computer vision, NLP, recommender system, genomics, drug discovery, just to name a few, and is really enabling critical business automation in many industries. While some application domains have progressed, different application domains have progressed at different rates. If you look at some of the recent applications in NLP, one of the critical things you notice is that some of the key metrics for these AI models have grown dramatically in the past few years. So if you look at metrics like model size, and you look like metrics like model flops, you see about a 4 to 5 order of magnitude growth in those key metrics just in the past 3 years. This is an explosive growth, and obviously it has huge implications on the kinds of systems you design and on the kinds of, for both training these models as well as deploying these models both in the data center as well as in edge platforms. Obviously, this challenge is exacerbated by the fact that, as we have talked about in multiple talks before, silicon performance is saturating. And so to keep up with this explosive growth in performance requires innovations across the stack, and specifically bringing forward new ideas that could help us bridge this performance gap between where data scientists think deep learning needs to go versus what we can reasonably deploy with reasonable cost of ownerships. So to handle this critical challenge, teams around the world have invested heavily in approximate computing techniques. And the goal is to really improve the energy efficiency and the throughput of AI chips and systems, right? The basic philosophy here is that unlike the applications we've had for the past 50 years, either on the server side or mobile sides, where everything needs to be close to perfect, the idea here is that deep learning can leverage inexact computations, and then one could use that inexactness to basically build, essentially exploit that to build efficient hardware. So when you talk about, this is exactly the philosophy of approximate computing, and when we talk about approximations, there are lots of different kinds of approximations you can have. You can have techniques that are purely in software. That's what you see on the top part of this chart, either on the application stack or you figure out new ways to do algorithmic approximations. And of course, as you go lower in the stack, you start implementing some of these techniques in hardware. You can optimize the architecture. You can even build optimized circuits. And then you can go all the way down to the device level. Now, the critical way to think about it is that the top half of the stack, or the top portion of the stack, is purely in software. So it's for folks who are already building AI systems today, a lot of those techniques have already been exploited. But the critical thing to note as well is as you go to the bottom of the stack, you potentially have room to get many orders of magnitude performance gains. And the challenge there is that that will take some time because you're really going down all the way to the transistor level. So somewhere in the middle, you see the idea of using low precision based architectures. And the idea here is that basically building chips with low precision architectures can give us some significant gain in power efficiency and performance. And the fundamental idea here is that you can get a roughly quadratic improvement in performance and power efficiency. And this applies to both AI training and AI inference systems. So both kinds of systems can benefit from this approach. And while doing so, it's important that we preserve model accuracy. Because while you can build all these approximations into the hardware, most data scientists and folks who deploy these models care about some metric, and the most common metric they care about is accuracy for a given cost structure. So let me talk a little bit about where we are as an industry. So I talked about precision being a critical knob in AI system performance. And indeed, the AI hardware industry, including folks who are building GPUs and TPUs, have moved aggressively towards exploiting this technique. So prior to 2015, or prior to 2016, in fact, most of all of AI computations were done essentially on CPUs and GPUs using FP32 arithmetic. However, the industry has moved aggressively towards reducing the precision of training systems to 16 bits. That's what we refer to as FP16. And the precision of inference systems, and these systems could be both in the data center and in the edge, down to 8 bits, right? So let's talk about this a little bit. So if you look at the training systems, the reason to move towards FP16 is roughly there is a 4 to 8x improvement in the floating point 16 engines or AI cores compared to AI cores built with 32-bit arithmetic. And that is a significant motivation because training these models can take exceptionally long periods of time today. Now, I'll talk a little bit about where the industry is at. There's a little bit of a Wild West going on here, where you have many different floating point 16 formats to represent these different tensors that you see in deep learning. I'll talk about that in the next chart. And obviously, these have implications on both hardware and software. On the other side of things, on the inference side of things, you can either do inference in 16-bit arithmetic, or you can do it in 8-bit arithmetic. The advantage of doing 16 bits, fundamentally, is that you already have a model that's trained for 16 bits, in 16 bits, so you can directly deploy it without having to worry about scale factors and various other issues. But of course, going to 8 bits is exciting because you get an additional 2 to 4x in throughput and energy efficiency and performance compared to 16 bits. But it incurs some challenges, and specifically those challenges include what are all the techniques one can use to take those 16-bit trained models and then convert them to 8 bits without losing any accuracy. So let me talk a little bit about the different 16-bit training options that the industry has deployed across various platforms. So I think I mentioned that this is a little bit of a Wild West, and there are 3 different floating point formats for 16 bits that the industry has pursued. There is the traditional IEEE floating point 16 format that has existed for decades, in fact. There is the bfloat 16 format that was proposed by Google. And there's a DLfloat 16 format that we at IBM, working with our partners and ecosystems, have proposed. So the way to think about them is they're all 16-bit formats, essentially. And you can see the number representation on the right side of this chart. And the way to look at it is that all 3 formats are fundamentally trading off mantissa bits for exponent bits. If you look on the one side, the IEEE format, which has just 5 bits of exponent and 10 bits of mantissa, and the bfloat 16 format swings it all the other way, which is having a lot of exponent bits, 8 bits, and just 7 bits of mantissa, and then the DLfloat 16 format that we pursue in our hardware is somewhere in the middle. Now, this is quite important because if you look at these different formats, they have trade-offs in terms of what is enabled in hardware and what's enabled in software. So for example, if you're doing training and you use the IEEE floating point 16 format, you just have 5 bits of exponent. so you don't have a huge dynamic range. To improve the dynamic range, this floating point unit now has to support essentially denormal numbers. And to do that, you essentially increase the energy consumed in those floating point units. You also have to develop techniques in software to make sure that all the tensors that you see in deep learning can be scaled to the appropriate range. That's a really important piece. On the other hand, if you look at the bfloat16 format, you have enormous exponents. You have 8 bits of exponents, so you can represent gradients in the 2 to the 256 kind of range. But the challenge is, since you have only 7 bits of mantissa, fundamentally, you have to do accumulation in larger precision. So in other words, you would have to do accumulation in 32 bits. So the way we think about our format, which we call DLFloat16, or Deep Learning Float16, is it kind of is the middle of both worlds. We don't need to support denorms because we have 6 bits of exponents. And at the end of the day, we still accumulate only in 16 bits, so we can have the best of both worlds in terms of not having to support denorm numbers and having to basically accumulate in low precision arithmetic. To give you a sense of how this plays out, this is a chart that talks about how our format works on the algorithmic side, on the hardware side, right? So if you look at the top left, you see these deep learning models, and these are essentially standard models. This work was done back in 2017, and you can see here that fundamentally you can get excellent model convergence for training for networks that were pretty state-of-the-art back in 2016, which is like ResNet 50. Now, if you look at some of the newer models, and you compare the different formats, you can see that as you lower the accumulation precision to 16 bits, you can see that fundamentally there is a gap that you see in terms of the model accuracy with the different formats. And in fact, our model format is about 0.5% better, which is really critical for some of these applications. Now, on the hardware side, if you look at the bottom right, you can see that exploiting these advantages I talked about on the previous chart, no need to support denorms, accumulation of lower precision. You can actually get, even in a relatively backdated technology node like 16 nanometers, you can get pretty high energy efficiency, 1.3 TOPS per watt, which actually is 30 to 50% better in some of the other formats. So let me take it to the next level here. So the question is, 16-bit works really well for training, 8-bit works really well for inference, and this leads us to the inevitable question, is there more? Can we scale precision further to be able to further improve the performance and power efficiency while preserving model accuracy? So this is basically the question that IBM, in collaboration with various universities and our partners in the AI Hardware Center, have been leading in the past decade. So our key philosophy goes as following, right? So we had Moore's law of scaling that took us through 30, 50 years of technology scaling, and that improved performance and power efficiency for a long while from generation to generation. Similar to that, we are proposing the idea of having a precision scaling roadmap, where essentially the goal is to figure out new techniques, new number representations, new hardware software co-design approaches that will allow you to scale the precision of these systems from 32 bits down to 2 bits or even 1 bit, while preserving model accuracy. And so this is the journey we've been on. And essentially, this is what we proposed back in 2016. And of course, the advantage would be, as you can imagine, as you go from 32 bits down to 2 bits or 1 bit, you can get an enormous performance gain that comes purely from the fact that these Mac engines that dominate these kinds of hardware are basically very efficient at low precision. Now, this was back in 2016. This was just a proposal. And of course, what has happened is a lot of folks across academia and industry have worked together in the past 5 years to enable some of these key advances. So if you look at the roadmap here, the green one corresponds to training precision. The y-axis is, by the way, bit precision. And the x-axis and the blue curve corresponds to inference precision. And you can see here that essentially what we proposed is you can scale precision by roughly 2x every 3 years, which gives you roughly a 3 to 4x improvement in computational throughput. And you can see here that if you look at the spots here, that in 2018 and 2019, we had quite a few advances in the industry that focused on how you can enable 8-bit training and 4-bit inference. This was the first step to go beyond the current systems. These are all research advances, so obviously it will take a few years for them to show up in products. And likewise, in just last year and this year, we have seen a lot of key advances that have enabled even lower precision inference and training. So I think these are really exciting because these advances allow you to preserve AI model fidelity, but at the same time, essentially dramatically improve the performance and power efficiency of the hardware. What I hope to do next is to walk you through some of these key advances that's really driving the leading edge of AI, and to kind of give you a sense of what's coming down the road. Let me start with training. Training was really focused on 16-bit, as I mentioned before. But in 2018 was the first year where there were two groups focused on work that enabled 8-bit training. So this was a group from Intel that did that piece of work, and a group from IBM, our team, that did that, the complementary work as well. Our work was focused on essentially using floating point numbers to do 8-bit training, and this is what you see here on the right side, which is what we refer to as DL-float8, 8-bit floating point numbers. And our key advantage was that all the tensors that you see in deep learning, weights, activations, and gradients, they are all represented in this floating point 8 format. And a lot of these advances use some of the techniques that NVIDIA had developed on previous generation of 16-bit training techniques. So we leverage those as well to make sure that these models can converge at 8 bits. We also used a couple of new ideas, and those ideas were central because when we talk about 8-bit representations, that's just a representation. But when you do a MAC, you have to accumulate the data. And we figured out ways to do accumulation in 16 bits as opposed to accumulation in 32 bits. That, as you can imagine, improved the energy efficiency of the hardware. So combining all of these different techniques, you can see here that fundamentally we ended up, even for pretty good models like ResNet 50, we ended up with extremely good accuracies while making sure that all of the computations in this model work entirely with 8 bits. What we noticed, though, is that the work that I showed before works really well for ResNet 50. But if you look at more models, if you look at more complex models like transformers, or if you look at more constrained models like mobile nets, you can see fundamentally that there are challenges. And you can see that the FP8 I talked about in the previous chart results in a significant loss in accuracy. So what this means is there was a new piece of work that happened in 2019 that was published at NeurIPS that talked about the concept of hybrid FP8. And the key idea here is that it turns out we cannot use a single representation to represent all of the tensors. You can use it for weights, activations, and gradients. So what you have to do is to pick one format for these tensors that care more about fidelity, more about precision, and one separate format for essentially gradients, because gradients need a higher exponent because the dynamic range is higher. So we coupled that with a couple of new ideas as well, and it appears that this technique, where you have two different floating point numbers used together, can essentially solve the challenges we saw with the original floating point 8 idea. There were a couple of advantages that we saw with this technique. Now, when we looked at this hybrid FP8 idea, we studied it on a whole suite of models: transformers, mobile nets, object detection, speech models, and we noticed that it worked exceptionally well across the model spectrum. And what's really nice is the industry is moving towards this direction. And we have seen recently work from Tesla that leverages the same hybrid floating point formats to build more efficient training hardware as well. So at this point, looking at the floating point 8 support, we can safely say that floating point 8 is an extremely robust format, and it works really well across the model spectrum. So after that point, what we did is we tried to figure out, OK, so we have these hybrid FP8 concept. We have two different floating point 8 formats. What is the implication of building this in hardware? So in this particular thing, we showed a chip that we built. It was really a multi-core chip, which essentially leveraged, built hybrid FP8 in hardware. Now, one of the challenges you can imagine is you don't want to build two different kinds of floating point units. You have two different formats, and essentially, you don't want to have dedicated units for each of them. So the way this was done, it was a very neat idea where you combine both formats into a larger format, which is a 9-bit floating point format. And essentially, when you build it in hardware, essentially everything executes as 9 bits. But when you talk about representation, you have it at 8 bits. The additional advantage we noticed is that you could easily build a hardware with this FP9 and combine it with the hardware that you already have today for FP16 for probably something as low as 5 to 10% overhead. So that was a critical, really nice piece of work, because what it showed you is you could build one piece of hardware that supports floating point 16, it supports floating point 8, and both the different floating point 8 formats. And you could get roughly about 2x the energy efficiency of training systems. So going from floating point 16 to floating point 8, you can see roughly a 2x improvement in system throughput. Now, there's a lot of work that's happening in the industry right now focused on how do you further improve this gain? Can you get to a 4x? And there are lots of ideas being proposed and debated at various conferences that certainly can point you guys to. But really a very, very interesting direction, because this work combined with the previous couple of charts shows pretty convincingly that you can actually build this hardware and essentially have AI models converge with excellent accuracy. I won't spend a lot of time on this chart, but I wanted to give you a perspective of what's coming down the line for even lower precision training. So starting in 2020, there were, again, a flurry of papers published at leading AI conferences focused on how do you either make 8-bit training more robust, or how do you scale training down to the 4-bit regime. And there were a couple of papers at NeurIPS last year. One of them was our work, which really focused on a floating point 4 format. Now imagine 4 bits, right? How do you use 4 bits effectively to do deep learning training? Well, lots of neat ideas here, including figuring out how to use radix 4 representations, new ways to represent gradients, scale gradients, and things like that. And what we also showed at NeurIPS was that if you actually built this, you could get roughly a 7x improvement over floating point 16 hardware, or roughly a 3 to 4x improvement over floating point 8 hardware. There were also lots of exciting work in this space that focuses on how do you statistically analyze these schemes? How do you develop these schemes? How do you figure out ways to optimize them? Now, these are all very early pieces of work, and I would imagine this 4-bit training is really where 8-bit training was 3 years ago. So this is a very active area of research, and a lot of it is we are engaged in collaboration with academia and industry. So if there's a lot of interest in this space, please do get in touch with us. Now, I do want to point out one interesting thing here. One of the motivations to go towards 4-bit training systems, besides building more data center efficient chips, is now the energy efficiency of training can be made low enough that you can actually deploy training at the edge. And that essentially opens up a whole new spectrum of applications that you can do for training at the edge. I'm going to pivot from training to inference. As I mentioned before, today the state of the art uses both 16 bits and 8 bits for inference. So FP16 deployment is the most common approach that you have today. And the advantage is, obviously, you train the model in 16 bits today. You have GPUs to do that. And you don't have to do any quantization. You can just take that model and you deploy it in whatever platform you need to deploy it at. And so that's a very significant advantage that you have at floating point 16. Of course, it's not as efficient, right? So there's a lot of work that's happened in the industry focusing on 8-bit deployment. As I mentioned, int8 deployment essentially is roughly about 2 to 4x better than floating point 16. So that's really nice. But you need to figure out ways by which you can quantize the 16-bit weights into 8-bit formats. And there are 2 different ways of doing that. One is through this technique called post-training quantization, where you train the model in 16 bits, and then post-situ, you figure out ways to convert it either statically or dynamically to 8-bit representations. This is the most common way of doing stuff in the industry for 8-bit deployed systems. But in parallel, there's a lot of groups that are investigating this technique called QAT, which stands for quantization-aware training. I'll talk about that in the next few charts, but the basic idea is that you have to retrain your entire model to take into account the quantization that comes from quantizing weights and activations, and you account for that error, and you modify the weights And basically, by doing that, you can deploy the weights in 8 bits without losing accuracy. It's kind of hard to read this chart, but I think the critical point I make here is that for most models, the pure post-training quantization, which is an offline process, in some sense, doesn't work too well. But if you use quantization-aware training, you can actually recover most of the accuracy loss that you see, even for very constrained models. So this is how you deploy models today in 16-bit and 8-bit. Let me talk about how we go beyond that point, right? So we talked about QAT, or quantization-aware training, for 8 bits, but really that is the only technique that's available today to deploy 4-bit models and below, right? Now, this is a really important piece to note because, as I mentioned, the way to build these 4-bit models so you can deploy 4-bit models is you have to train the entire model again with these quantization losses. What this means essentially is you have to physically quantize the weights and activations of a network in the forward phase of the training so that you can essentially account for those losses that come from quantization and then backpropagate it and update the weights. Now, I won't go into the details of all the different schemes and techniques that enable this today, but I think it's really important to note that there have been quite a few ideas here to enable this QAT process. And these have to do with how do you specifically quantize weights and how do you specifically quantize activations. The specific thing here to note here is one of the ways that the industry has moved forward in this domain is to really enable mechanisms by which these quantization schemes themselves can be learned as part of the training procedure. So again, a lot of exciting ideas here. There is an entire ecosystem of players focused on building these quantizers. And every few months, you have a better quantizer that gives you a more accurate set of models that you can then deploy in your edge devices, for example. To give you a sense of the state of the art, this is an example of what we see today in Int4. So this is how do you build an Int4 model and what accuracies do you get? So what you're seeing here is 4 domains. On the top right, you have vision. On the top left, you have object detection. On the bottom left, you have transformer models. And on the bottom right, you have speech models. And across these different models, what you're seeing is the floating point 32 models. That's the second column in here, for example. And if you compare that to the Int4, these are the 4-bit weights, you can see basically excellent accuracy across the model spectrum. So except for one model, the accuracy on an average is only about 0.5% from the baseline, which is quite impressive. Now, what it tells you is I can now deploy these models in data centers and in edge to basically have much more energy efficiency compared to 8-bit deployed models and 16-bit deployed models. Now, what happens here is that we've been talking about the idea that you have to retrain the models so that you can get efficient quantized models, as I showed in the previous chart. But there are a bunch of challenges here. And those bunch of challenges have to do essentially with how do you essentially build these models, how challenging it is, what are all the challenges that go with it. And by the way, when we talk about 8-bit training or 4-bit inference, there are still a fraction of the layers, and that's roughly about 10%, that are sitting in a higher precision. And that's sometimes a challenge because your lower precision hardware is so efficient that your higher precision compute starts to limit the gains you can get. So a lot of exciting work happening in the space focused on addressing some of these critical challenges. And of course, the industry is also simultaneously moving towards understanding how we can lower the precision even further, especially for weights. Because as I showed you in the first chart, the weights are growing substantially. So can we reduce the weights down to 2 bits or even 1 bit while keeping the activations at higher precision? So lots of exciting challenges. An entire set of research community is working on these challenges. And I fully expect some of these advances to fully materialize over the next few years. I talked a lot about algorithmic resilience. I talked about 16 bits. I talked about 8 bits and 4 bits. But realistically, the question that one asks is, from an algorithm's perspective, that's great. What is the real benefit you get in hardware? And that's kind of what all of us are really interested in. So to address that question, we actually built custom hardware back in 2019. This was actually an AI chip that we built, basically having a multi-core system. And each core had all of these aggressive, low precision formats that I talked about on the previous chart, right? And this work was, for those of you who are interested, was published at the Circus conference earlier this year. And as you can see here, as you go from 16 bits down to 8, down to 4, down to 2 bits, you can get an enormous gain in energy efficiency. So you go from about 2 to 3 TOPS per watt up to 40 TOPS per watt. And so this validates the idea that you can actually do hardware-software co-design, you can build these ultra-low precision AI models, and you can deploy them and get significant advances in terms of energy efficiency. I think many of you might be familiar with the Lindley Group. This is a group that actually does a lot of analysis on CPUs, GPUs, AI chips, and they analyze our AI chips, and they looked at them, and they confirmed the advantages of some of these new data types for preserving accuracy, and confirm that it preserved accuracy while giving us the energy efficiency and throughput gains that we would expect. Now, this is all from a research perspective, right? Now, if you look at the product point of view, in hot chips, just a couple of months ago, we introduced our first product called Telum. And Telum essentially is an embodiment of all of the work I talked about, but integrated into a leading edge CPU. So Telum is essentially takes some of these AI accelerators and basically builds a state-of-the-art chip. This is a 7 nanometer chip running at 5 gigahertz, and basically integrates 5 gigahertz CPU cores and 2.5 gigahertz AI cores put together to enable essentially a whole range of AI applications focused on real-time AI insights. I'll talk more about this in the next chart, but these advances really have enabled us, at the end of the day, to have extremely high teraflops per system, and of course, at the same time, enabled very low latency AI inference. To give you a little bit more insight into what Telum does, so IBM's primary enterprise business is focused on markets that are either in banking, in insurance, and of course, Fortune 500 companies, where a lot of these companies come to us to build them resilient infrastructures. And in this particular case, what we showcased essentially was that by integrating AI cores on the same die as CPU cores, we can essentially enable very low latency inference. Now, there are a whole host of AI applications that are enabled by this advancement. I'll give you one example of that. Imagine you're swiping your credit card, right? That credit card goes back to one of our systems, and basically you have to respond within about 10 milliseconds. That's your window of your transaction. Now, what you want to do is within that 10 millisecond, you want to run a really complex AI model and confirm that the transaction is not fraudulent. So that requires essentially very low latency AI working essentially on the same die as your CPU and doing all of this work really within a fraction of a millisecond. That's what we've enabled using Telum, which will be available next year. And one of the critical requirements from our clients is to be able to do all of that in a way that preserves enterprise-grade security, virtualization, and protection, right? So one of the challenges you have with AI chips today is you don't have enterprise-grade protection. If you are on a GPU, very likely you can access other processors' memory. So from an enterprise point of view, this kind of an accelerator, tightly embedded, allows us to build systems that are very resilient, highly secure, and enable low latency AI all at the same time. I also want to throw this as an example because what we are seeing is happening is across the application space, whether we talk about enterprise or whether we talk about edge, essentially people are building custom hardware, and those custom hardware have very different needs, right? And essentially we are seeing a lot of different forms of chips being built. It's not just going to be an AI chips talking to the processor, it's going to be AI chip tightly coupled to a processor to do some tasks that it couldn't do by itself, the CPU couldn't do by itself, or the AI chip couldn't do by itself. I want to spend about maybe 5 minutes talking about where do we go from here. We talked about 8-bit training, we talked about 4-bit inference, but there's a lot of work happening in the industry around further reducing this precision down to 4 bits and 2 bits. So 4 bits for training and 2 bits for inference. Lots of great work happening in the research domain, lots of work happening to build these things into hardware. So very exciting space to be in. And certainly if anybody is interested, I'd love to collaborate with you on that. There's a lot of really exciting work that was done by NVIDIA on sparsity. And sparsity leverages the fact that basically you have a lot of zeros, right, in your compute are certainly in your weights. And the question there is, what is the most effective way in hardware to leverage the sparsity? And one of the questions we ask is, can you combine these techniques? Can you combine training or inference at low precision down with sparsity? It's not yet clear, and that's an open set of questions that the community is working on. Now, when you build hardware with very low precision and sparsity, you have to worry about architectural issues. The reason is because traditional architectures, including GPUs, don't do it so well when essentially you have so much parallelism. So the question here is, could you improve the utilization, the net customer visible performance of these AI chips by exploiting new forms of parallelism? And this really goes into that regime of hardware-software co-design, building a compiler stack that is completely tightly coupled to the hardware, and so on and so forth. And finally, I must mention that there are lots of research communities around the world focused on analog computing approaches and really figuring out what is the right material to do analog computing, and does it really work well with some of these aforementioned techniques. So in my view, I think looking at some of these key ideas, we certainly feel that there is a good opportunity to improve the performance of AI compute by an additional, give or take, 10x or in the next 3 to 5 years. The previous chart focused on compute. This one focuses on bandwidth. It turns out that improving computational efficiency is great, but a large number of popular AI models, especially not in benchmarks, but actually deployed in real life, are actually bandwidth limited. There are lots of examples of those. For example, if you build AI chips today, they have an on-chip SRAM that's roughly 64 to 100 megs. And what it means is if you're building a really large model, that model is sitting in your DRAM, and essentially pulling that model from the DRAM takes a lot of energy and takes a lot of latency. And this is, by the way, in spite of the fact that we have HBM stacked DRAM, which has pretty high bandwidth, right? Similarly, if you look at a lot of the recommender systems that are used by Facebook and Google and Amazon, they have large embedding tables. Those embedding tables can be hundreds of gigabytes, sometimes even terabytes. And those recommender tables have to fit into memories of AI chips, which again becomes really hard to access. So a lot of excitement around graph neural networks. This is really where you're trying to put together a graph that is either for social networks or for drug discovery, many such applications. These directly drive, in some sense, they drive sparse computations, sparse lookups, and so on and so forth. So the one possible solution to all of these challenges is to really have 3D stacking on top of the AI cores. This is different than HBM. HBM already exists today. This is really saying by putting 3D memory, that's SRAM or DRAM, directly on top of our processors, we can improve the bandwidth by an order of magnitude, and therefore improve the performance of some of these applications significantly. So very, very exciting area to go, and it's really needed, especially if you improve the compute throughputs like I described on the previous chart. So to put it all together, I just wanted to highlight what the road ahead looks for AI systems. I talked about the next generation AI chips, leveraging analog computing, sparsity, very low precision. You can get a net compute gain and 3D, of course, for bandwidth. You can see a roadmap where you can improve the performance by 5 to 10x. But a lot of exciting work is also happening in basically building new systems for AI that are not just perception limited. So for example, how do you explain what's happening inside an AI model? This is what we refer to as explainability. And essentially putting together systems that can reason about what the right approaches are. And there is a lot of exciting work happening at the intersection of putting together these traditional AI that we refer to as neurosymbolic AI, together with these deep learning approaches and these graph neural nets to basically build new reasoning systems that are much more efficient than the ones we have today. Obviously, these systems look very different than what we currently deploy today, so we'll drive new architectures, new chips, and certainly a lot of exciting work for all of us in the decade ahead. And finally, I want to make a point about security, and that comes about because there's a lot of interesting intersection happening between AI and security. This is not just about applying AI for security applications, but it's really about building hardware, building AI chips that are fundamentally secure end-to-end. So encryption being a key example, understanding side channel attacks on AI systems, figuring out how do we do homomorphic encryption for AI systems. Lots of exciting problems to be solved there. So I would say that it's a lot of exciting work that's happening in all of these domains, and certainly if any of you are interested in it, would love to talk to you more about it. With that, I want to thank all of you for attending my talk. If you have any questions, please feel free to visit us on the AI Hardware Center website or get in touch with us. We'd be happy to talk to you. Thank you.
When it comes to the lower precision models like Int4, are they portable at all? Or does retraining have to be done each time? And are they hardware specific, or do the common frameworks support things like that?
Great question. So they are not portable to the extent that each new model you need to deploy, you need to train them. So there is a certain training cost associated with these models. So you have to make that cost of ownership judgment, right? That you're going to spend money on a bunch of GPUs, and on the other hand, you're going to be deploying them, and the deployment is much more efficient. So there is that trade-off that one has to keep in mind. So for example, in applications where you see the model lifecycle is really small, you have this couple of days, you don't have time to do these quantization-aware training, so you end up in situations where you would just deploy at higher precision, right? The other question was with regards to, does it depend on the hardware, right? It doesn't. We deploy these systems on our own hardware, we deploy them on GPUs, and they work just fine across the board.
I'm Sumit from UW-Madison. So you talked about that edge hardware. Now when you say edge, and also you talked about like those ResNet 50 and all, so how much area of the chip you are really targeting, let's say for ResNet 50?
It depends, right? I mean, again, a lot of the work I talked about is actually data center, but you could deploy some of these ideas on the edge. To answer your question, edge is non-monolithic, right? You can have, edge could be this, edge could be your car, edge could be an edge server situated at the end of a data center. And these are very different constraints, right? If you have in a mobile phone, you probably have tens of square millimeters of silicon at most to devote to AI. If you look at an automotive chip, you can have a few hundred square millimeters to AI. And if you look at the edge of the data center, or which is what we call the network edge, that really could have 300, 400 square millimeters of silicon. So there are different, I mean, obviously each of these domains have their own cost of ownership arguments and cost of, total cost of ownership arguments that defines the size of the silicon and how much they can do at the edge versus how much they would require to be done at the data center. So it depends a lot on definition of edge, but at the extreme edge, the IoT edge, it becomes, you really don't have a lot of silicon space to play with, which by the way is also why some of these techniques are attractive, because the area also scales down dramatically when you build these low precision engines compared to higher precision engines.
One more question. So
Sure.
You showed that when you trained the network in, let's say, 8-bit and you moved to 4-bit, there is no degradation in accuracy. Like, what's the exact reason?
So yeah, sorry, let me be clear. So you're talking about this chart, right? You're talking about the training chart, this one?
Yes.
Okay. So this one focuses on two things. One is on the one column focuses on 32-bit arithmetic. This is the thing you do today. You can deploy a model at 32 bits. That's no training. It's just your existing model. You already trained it for GPUs. What is the precision of what is the accuracy of the model? That's what you're seeing. Sorry, I'm trying to find my mouse here. This one, right? This one is what it does, it leverages these quantization-aware training procedures. What it's doing is you are retraining the model, considering the fact that you have all of these issues, the issues associated with the quantizing the weights, quantizing the activations, and you compensate for that by modifying the weights through the standard backpropagation procedure. So this is really a correction mechanism where you have errors that came from quantization and then you compensate them back to build these models. And essentially the way to think about this is you have, at the end of the day, a metric. At the end of the day, what you have is ways to, in a deep learning application, you have ways to modify the weights depending on what your loss was, what your error was. This just adds an extra dimension to that compute. And basically by doing this, you not only compensate for traditional neural network convergence issues, but you're also compensating for the inaccuracy that comes from weight and activation quantization.
Thank you for the great talk. I'm Rob Tinson from University of South Carolina. I just have a follow-up question about the question that our friend asked. So the thing that we're doing here to just make sure the backprop is the backward path is full precision floating point, right? The forward path is quantized.
For the inference work that's in 4, yeah, that's exactly what we're doing. Correct.
Okay. And also I have a follow-up question for myself.
Sure.
It's a common practice that there are different layers in deep learning and they have different importances.
Right.
So in most well-known papers in the quantization area, we know that in the beginning we go with the full precision, then in the middle we
Right.
don't really care about it, which lead to mixed precision optimization, implementation. So I just want to know your insight about this, and also in slide 14, do we have similar thing, or the entire thing is integer 4-bit, or like the first layer is floating point, and then the layers after that is 4-bit?
Okay, great question. So let me try to answer them. Make sure I don't miss anything here. So first is, I mentioned that there is a subsection of layers that has to be done in higher precision. That's typically in the range of 5 to 10%. In those layers that you basically use 8 bits, in the remaining 95% of your compute, you're using 4 bits. How do you define that? How do you know that? And that is essentially a set of heuristics that we have developed in time by analyzing a whole spectrum of networks. We're showing you a subset of what you're seeing here, but essentially analyzing all these different networks, you get some basic understanding of where things fail, and you put them into a set of heuristics so that when you quantize it, you don't quantize everything, you only quantize a subset.
So what percentage of these models do you think are implemented on average on full precision?
On full precision? Nothing in full precision. About 5% in roughly in 8 bits, and the remaining 95% in 4 bits.
Okay, so nothing full precision, everything. And even in the training, you have this mixed precision.
Correct.
Too, right?
Yeah, even in the training, we have mixed precision as well, where we would, most of the layers work in FP8 on the previous training work, and maybe about few percent, I would say 3 to 5% is in FP16.
Thank you so much.
Sure.